Okay, so in this video I'm going to have a look at the Leaving Cert Maths Higher Level Paper 2 for 2017, and I'm going to have a look in particular at questions 5 and 6. So this is question 5 here, and we have this shape here, this rectangle, and inside it we have some triangles and this quadrilateral here. So let's see, we're given various dimensions here and they're actually all written in here. So the first thing we've got to do is prove that the triangle AFE, so this little triangle here, and DAE, this triangle here, these two triangles in other words are similar. Now really what we're going to, this is really part of the proof for Pythagoras' theorem that you may have done in junior cert. It's one of many proofs for Pythagoras' theorem, but what we're going to do here is take this triangle here and prove that it's similar to this big triangle here. Then we're going to take this triangle here and prove that this is also similar to this big triangle here. So if they're both similar to the big triangle, in other words if they both have the same size angles as this big triangle, then they must have the same size angles as themselves. So in other words these two triangles here must be similar. So let's start. Now first thing is we're going to have a look at AFE and AFD. So AFE, so we're going to have a look at AFE, this triangle here, this little triangle here, and the big triangle here. So first thing we want to do is say that the size of the angle AEF, that's going to be equal to the size, so in other words this angle here is 90 degrees, and also FAD here, that's equal to 90 degrees. We're given that in the question, we're told, so that's given. So this is 90 degrees and this is a rectangle, so we know that this angle here is also 90 degrees. Now we can also say that the size of the angle AFE is equal to the size of the angle AFD. Why? Because they're common angles. It's a common angle, in other words. This angle here, in other words, is in both triangles. So therefore you can say that triangle AFE and AFD are similar. Now we've only shown that two of the angles in each triangle are the same, but if two angles in two triangles are the same, the third one must be the same as well, because there are only three angles and they add up to 180. Okay, so we've shown that this small triangle is similar to the big triangle. Now we're going to take this triangle here, AED, and show that it's also similar to the big triangle. So we can say that angle AED is equal to FAD. So AED, this angle here, is equal to this angle here in the big triangle here, FAD, equal to 90 degrees. Again, we're given that. We can also say here that ADE in the small triangle is equal to ADF in the big triangle. So this angle is equal to this angle. Again, it's a common angle. So therefore the triangle AED and ADF are similar. So if this triangle and the big triangle AFD are similar, and this triangle and the big triangle AFD are also similar, then these two here must be similar. So therefore we would say that the triangles AFE and AED are similar triangles. Okay, So the next thing we've got to do is find the length AD. So find the distance from here to here, this distance here. So I'm going to use the fact that this triangle and this triangle here are similar to find this distance here. You got to remember that when triangles are similar, their sides are in proportion. So let's just draw the two triangles first. So I'm going to draw the small triangle here first, and then the other one, the bigger one. So we have AFE here, A, F, and E, and we have D, A, and E here. Now in this triangle here, we know that this side is 5, and we know this side here is 12. So what I'm going to do here is just use Pythagoras' theorem here to work out this side here. You may have spotted already that this is going to be a 5, 12, 13 Pythagorean triple, but really what you do here is just say AF, the distance from AF squared is going to be 5 squared plus 12 squared. So when you work that out, it's fairly straightforward. Just square this, add them, and get the square root. You will get 13. So this distance here is actually 13. So now I'm going to use the fact that sides are in proportion. By the way, we also know that from A to E here is 12. So sides are in proportion here. So I'm going to say 5 over 12. In other words, this side here in this triangle over its corresponding side 12 is going to be equal to this side here, which is AF. So it's 13 over its corresponding side AD, which is what we have to find, AD here. So we have a fraction equal to a fraction here, so I'm just going to cross multiply here. So it's 5 times AD is equal to 12 times 13, and then the distance from A to D is equal to 12 times 13 over 5. When you work that out, you get 31.2 centimeters. Okay, so 31.2 is this distance here, 31.2 centimeters along here. Okay, so let's move on to the next part of this question. So we're told that AFE and AGB are similar. Show that AB is equal to 36. So in this particular part of the question, we're told that this triangle here, AFE, and AGB, this big one here, AGB, that these are similar. So this triangle and the big triangle that it encloses, they're both similar. They both have the same size angles. So we've got to find AB, the distance from A to B down here. So we've got to find this distance here. So let's just draw the two triangles separately first. So I'm going to draw AFE first. That's the small triangle again. AFE, AF, and E. And we know that this is 5, this is 12, this is 13 here again. And let's draw the other one then, the bigger one here. This one encloses that small one. So this is A here, this is B here, and this is G here, and we know that this is 39 here. It's 39 because it's, I've drawn it the other way around, but it's this side here is 12 plus 27. Okay, so we've got to find AB. So we've got to find this distance here. So its corresponding side is this 12 here from A to E. So let's just write all this down again. So we're going to say AB, the distance from A to B, over 12. So this distance over 12 is going to be equal to, well, we have to use 39 here over its corresponding side, which is 13. So let's just multiply this across again. So we've got 13 times the distance AB is equal to 12 times 39. So that just gives me AB here, the distance from A to B here is equal to 12 times 39 divided by 13, so that just gives me 36. So we've shown that AB, the distance from A to B here is 36. Okay, so now we've got to find the area of the quadrilateral GCDE. Find the area of the quadrilateral GCDE. So that's GCDE. So this quadrilateral here, we've got to find the area of this. So the way I'm going to do this is, we know that this length here now, by the way, we've just worked that out, is 36. So that distance there is 36. And we have it on this side as well, 36. from A to B. So what I'm going to do is find the area of the entire rectangle, then I'm going to find the area of this triangle AGB, and then I'm going to find the area of this triangle here, which is AED. I'm going to add the two together and subtract from the area of the entire rectangle. So I'm going to find the area of this triangle, the area of this triangle, add them together, subtract from the area of the entire rectangle. So let's just work through that. Okay, so the area then, the area of the entire rectangle is ADCB. ADCB, well, that's just the length times the width, which is 31.2 times 36. So when you do that, you get 1123.2 centimeters squared. Now we're going to find the area of these two triangles. So the area of triangle AGB first. AGB. So it's going to be half the base times the height. So that's going to be half the base, which we don't know, that's BG, times the height we do know, that's 36. So the base we're going to work out using Pythagoras' theorem. So I'll just do that bit over here. So we know that, so just to go back to our diagram again here, I'm trying to work out this distance here from B to G, GB here. So I know this distance here, I know this distance here, so I'm going to use Pythagoras' theorem to work out this distance here. So the way I'm going to do that is I'm going to say 39 squared, that's the hypotenuse, is equal to the other side squared, which is 36 squared, plus BG squared, BG squared here. So again, you can just do this fairly quickly on your calculator. Square 39, square 36, subtract them, or in other words, bring this over, subtract 36 squared from both sides, and you get, and then square root, so you get BG, the distance from B to G is 15 centimeters. So 15 will go in here. So that'll give me, when I multiply these three together, I get 270 centimeters squared. Okay, so that's one triangle. Let's find the area of the other triangle. So the area then of the other triangle is AED. AED, so that again, that's going to be half the base times the height. So it's going to be half the base here, which is 12, and then the height we don't know. So if we go back up here again, remember it's this triangle here. This is my base, which is 12. This is the height here, which I don't know, which is ED. So I'm going to have to use Pythagoras' theorem to find this as well. So I'm going to square this, and subtract them to find this here. This squared plus this squared is equal to this squared here. So I'll just do that again over here. So I have 31.2 squared is equal to 12 squared plus the distance from E to D squared, which I'm looking for. Again, you can do that fairly quickly on your calculators, but you get 28.8 centimeters. So that goes in here, 28.8 centimeters, and when you multiply all that together, you get 172.8 centimeters squared. So okay, I have the area of the entire rectangle, and now I have the areas here of the two triangles. So these are the three numbers I'm going to use. I'm going to subtract these two here from this one here. Okay, so the area then, the area of GCDE, which is what we're asked to find, the area GCDE is just going to be equal to the area of the entire rectangle, 1123.2. we got to subtract these two here added. We're going to add these two here, remember. So it's 270, and we've got to add 172.8. So look, when you do that, you get 680.4. 680.4 centimeters squared. That's the area of our quadrilateral. Okay, so that's it for question 5. Let's have a look at question 6. Okay, so question 6. Take the Earth as a sphere. So here's our Earth here, with radius 6,371. So this distance here is the radius of the Earth. Jack is standing on the cliffs of Moher at a point J, which is 214 meters above sea level. So this distance here, this little distance here, is 214 meters. I've converted that here to kilometers. I'm just going to leave everything in kilometers. So the distance from here to here is 0.214 kilometers. He's looking out to sea at a point H. So here's our point H. Take A as the center of the Earth. Find JH. So we've got to find the distance from here to here. Give your answer correct to the nearest kilometer. So you can see that this is a right angle triangle. This is one of the theorems that says that a tangent will meet a radius at the same point at the edge of a circle at right angles. So this here is a right angle here. So if I draw that, I'll get a right angle triangle like this. So here's my right angle, we'll put it here. So this is going to be H here. I'm going to put A up here, and this is going to be J here. So from A to H, so from A to H here is 6371. 6371 kilometers. From A to J then, the hypotenuse of this triangle from A to J here is going to be 6371, but also we've got this little bit up here which is 0.214 kilometers. And we've got to find the distance from J to H here, this distance out here. So again, I'm just going to use Pythagoras' theorem. So we can say that 6371.214, if we square it, that should be equal to the distance from J to H squared plus 6371 squared. So look, I'm going to do a couple of steps here. I'm just going to write down JH here squared. So I've done on my calculator this squared, I've done on my calculator this squared, I brought this over and I've subtracted, in other words subtracted this amount here from both sides, and I end up with 2726.8337 833796. Square root both sides then, so the distance from the J to H here, from J to H here is the square root of this here, which is 52.219, and we have to give our answer JH here correct to the nearest kilometer, so that's just 52 kilometers to the nearest kilometer is 52 kilometers. Okay, next one. So that's down here. Same question again. Really, it's the same. We still have the Earth, we still have a radius here, but we're told here, we're given some extra bits of information here. We're told that the point C here, which is where the cliffs of Moher are at a latitude of 53 degrees north of the equator. So here's our equator here. We're told that this is 53 degrees here. And we're told that S1 represents a circle that is at a latitude 53 degrees. So this circle here is at a latitude where the cliffs of Moher are 53 degrees north. S2 here is where the equator is. This is the equator. So that is at latitude 0. A is the center of the Earth here, and this point here is the center of S1. Now we're told that S1 and S2 are on parallel planes. So what I've done here is I've drawn this line from the center of S1 out to C here. We have this line down here, and we have this radius here as well. You can see this is this Z shape here. We know that this line here has to be parallel to this here because we're told it in the question. We're told that they're on parallel planes. So really what we've got here, I guess, is we've got two parallel lines here, and we've got a transversal going down along here. So these two lines are parallel. We're told that this is 53 degrees here, so this angle here must also be 53 degrees. So this is 53 degrees because they're alternate angles. So I put 53 degrees in here as well. Now we're asked to find then the length of the circle S1, this length around here. We know that the length of a circle is just 2 times pi times r. Now we know 2, we know pi is just a number, or is what we don't have. So we need this distance here. We need the radius of S1. So the distance from here out to C is what we need. And the way I'm going to do that is use this triangle here. This is a right angle triangle here. So I'm going to use that. So if I draw that here, I get this kind of a triangle here. This is C out here, this is A down here. I know this is a right angle here. I know the distance from A to C here is the radius of the Earth here. So that's 6371 kilometers. I know this is 53 degrees here, and we'll call this or here, this distance here, or. From the center here out to C is a distance or. Now I need or here. Or is the only thing I don't have in this formula to work out the length of the circle. So let's find what or is anyway. So the way I'm going to do that is use cosine. So I'm going to use the cos of the angle 53 degrees. The reason is because I need the adjacent and I have the hypotenuse. Adjacent over hypotenuse is cos of an angle. So the cos of 53 degrees here is just going to be or over 6371. So that just gives me or then is going to be equal to 6371 times the cos of 53 degrees. When you work that out, you get or here, the distance or is 3834.1635 and that's the distance in kilometers. So now we know this distance here. So all we've got to do now is put that in here to our length of a circle formula, and that will give us the length of our circle. So let's just do that down here. So the length, find the length of the circle S1. So the length of S1 is just going to be 2 times pi times this distance here, 3834.163513. When you do all of that, you get 24090 .75985, and we're asked to give your answer correct to the nearest kilometer. So here's our nearest kilometer here, so it's 2409. This is a 7 here, so we got to round this up to 1 kilometers to the nearest kilometer. Okay, so that's it for questions 5 and 6.